Transmission of electrical impulses. Electrical activity is a natural property of biological cells, although electricity is not really the right term here. In reality, it is electrochemistry we talk about when dealing with the electricity of the body. This means that the electricity comes from ions that are themselves electrically charged. When ions move from one place to another, usually across a membrane or down a membrane, this is where the electricity comes from. Even though it is chemical electricity, it can still be measured. This is why the ECG can pick up the electrical signals from the heart, because you can pick up such signals from nerve cells and muscle cells too. An electromyogram picks up the electricity that comes from the muscle cells, and a nerve conduction study picks up the electrical flow through a nerve. An EEG or electroencephalogram measures the electrical patterns in the brain. There are charged molecules throughout the body, but the ones that participate in nerve and muscle cells' electrical activity are mainly ions, usually charged atoms or small molecules. The ones you might be most familiar with are electrolytes. When you measure a person's electrolytes, you usually measure the sodium, potassium, chloride and bicarbonate levels. Calcium is an ion that is also essential in the heart, mostly because it is necessary for the heart muscle to contract. Let's look again at the action potential to see what we mean by absolute and refractory heart muscle contraction periods. An absolute refractory period is when the heart muscle cell can't be reactivated to make another action potential. This is a good thing because it means the heart can't just go wild and beat whenever it wants. You need this refractory period to prevent serious heart rhythm disturbances or arrhythmias. This image shows when the absolute refractory period is during the action potential. The absolute refractory period is a pause button on the heart muscle's ability to be restimulated to contract again, expressed as the amount of time it takes. During the absolute refractory period, the cell membrane's sodium and calcium channels are inactive, so it is impossible to start another action potential. The difference between the absolute and relative refractory periods is easy to remember. The absolute refractory period is when it is impossible to have any new action potential, while the relative refractory period is when there is a possibility that a new action potential could happen, but it would be harder to do. This period occurs right after an action potential moves down the axon, so it would have to occur by a larger than normal stimulus. The image doesn't show that when potassium exits the cell to cause repolarization, there is a period called hyperpolarization. It's when the potassium overshoots the goal and causes too much electronegativity in the cell. The cell could still depolarize during this time, but it would take a larger stimulus in order to do this. When the resting potential returns to normal, the relative refractory period ends. It isn't shown in the above image because it represents a regular muscle cell's action potential, but in pacemaker cells in the heart, such as the SA node, the action potential looks different. It has a certain threshold of 40 MeV that triggers the action potential to happen. Before this, there are the leaky sodium channels, also called funny sodium channels, that slowly leak sodium into the cell. When it reaches the magic threshold, both sodium and calcium rapidly enter the cell through different channels. The repolarization happens with a fast outflow of potassium out of the cell. These cells don't need a long break, as you see with the heart's cardiomyocytes' drawn-out action potential, because they don't contract, although they do hyperpolarize, as you can see, where the line drops below the threshold. These funny sodium channels start up and pace the cell's electrical output by leaking sodium back into the pacemaker cell.